Hello everyone. Thank you for joining this SimScale and Datadvance webinar on the CFD-Driven optimization of an industrial-grade compressor from your web browser. We'll be starting in just a few seconds. Thank you to everyone who's joined. First of all, I'll introduce the speakers today. So the first speaker is Laurent. He's the Vice President of Global Sales at Datadvance. Also from Datadvance, we have Nikita, an application engineer who's put together the technical side of this collaboration. And also, I will be speaking today. I'm Steve Lenne, and I manage the application engineering team here at SimScale. Okay, so let's get started. What are we going to look at in today's application? Well, we're going to be looking at how we can introduce a modern design, simulate, and optimize workflow into your product development lifecycle. So we'll have me and specialists from Datadvance presenting this design, simulate, optimize collaboration workflow that relies on simulation tools built on the latest cloud computing technology. SimScale, the only technical platform that can deliver the promise of liberating engineers from legacy software constraints and hardware limitations. And we'll be looking at a real-world case featuring the design optimization of an air compressor. And we'll be presenting the different elements of this live to you today. So what is the case that we're going to be looking at? It's an end-to-end shape optimization. Starting from the geometry is produced in Siemens NX, and it's a parameterized CAD model of an air compressor. This CAD model has 4 geometric parameters that can be controlled programmatically. That geometry is then passed through the API to SimScale to be simulated. And this is a CFD simulation using an incompressible analysis. And the relevant quantitative results of the efficiency of this compressor are then passed programmatically through the API to Datadvance's pSeven optimization tool. pSeven uses a surrogate-based optimization model to look at the temperature and pressure drop and obtain the highest efficiency impeller. Obviously, once this workflow has gone through once, pSeven chooses the geometric parameters to change on the CAD model to select the next design iteration and goes through the process again. So it runs the simulation and analyzes the efficiency. So we've got 4 geometric parameters. Say we want to look at 20 values per parameter. That would be 160,000 simulations that we would have to run in a matrix analysis if we were going to look at every single point. However, by optimizing this using the surrogate-based model in pSeven, we only had to run 120 simulations to find the highest efficiency impeller. So all of this is using desktop CAD and cloud-native CAE tools orchestrated via pSeven. For the actual simulation setup, here you can see the geometry where we have the boundary conditions. Number 1 represents the inlet into the impeller here, and we have air at 1 atmosphere coming into the inlet. And then the outlet flow rate for these simulations is set at 1.5 kilograms per second. And the outlet is seen at 0.2, so the largest diameter of the impeller. We've got a MRF zone, a multiple reference frame, and a rotation speed of 10,000 RPM for this rotor. And the physics that we're using are a compressible steady state simulation with fully turbulent flow. Okay, so that's the introduction to the case. I'm now going to give a brief introduction to SimScale, what SimScale is, and a short demonstration of the platform before I hand over to Laurent and Nikita for an introduction to the Datadvance pSeven side. So what do we do specifically here at SimScale? Well, we created the world's first engineering simulation platform in the cloud. And what does this mean? Well, with a traditional CAE platform, you require high-performance computing hardware that has to be purchased and maintained. With SimScale, there's no hardware, and there's no software to maintain either. It's completely software as a service. You just need a web browser to access SimScale. Also, with traditional CAE tools, there's high fixed costs for the software and the hardware. SimScale is cost efficient. There's no fixed expenses, and it's a usage-based pricing model. Also, with traditional CAE tools, there's typically a know-how barrier. So they're complicated pieces of software to use, and you require extensive training and knowledge to be able to use the software effectively. So you typically have a few experts in the organization that run the analysis. SimScale, on the other hand, is very easy to use with support and seamless collaboration to share projects worldwide. So let's look at the product design lifecycle for a moment. And SimScale provides a cloud-native, collaborative, end-to-end simulation platform that can support this product lifecycle. So traditional CAE tools are focused on the design validation, late-stage simulations, where you have a couple of experts, as I mentioned, using the software. They have seats for this software. If there's a HPC, there might be a job scheduler to control and orchestrate these HPC jobs, and on-premise hardware to actually run the simulations. There's an incentive to do early stage simulations so that you can iterate more on the design and make changes when the cost of change is low at the early stage in the design lifecycle. And there's obviously also other simulation initiatives throughout that design lifecycle, like design space exploration, digital twins, and advanced manufacturing, etc. So with SimScale, all of that job scheduler, on-premise hardware, etc. goes away. And we manage and provide a software as a service solution to all of that infrastructure. So the HPC orchestration, the licensing, the load balancing, the middleware, networking, storage, operating system, that's all managed on the cloud with SimScale. On top of that, we provide you with various simulation technologies that you require to solve the physics in your models. We support multiple physics from FEA applications, stress, drop testing, crush and compressing, to thermal cases, electronics cooling, conduction, heat transfer, and CFD cases like external flow, internal, rotating machinery, etc. So SimScale is a SaaS application that provides full collaborative access for CFD, FEA, and thermal applications. And crucially for today's application, we have an API that spans all of these physics, so you don't have to run everything through the user interface. You can programmatically run the simulations. So today we're specifically looking at rotating flows. We're running that through the API with the specific mesh technology to take care of that simulation as well. Okay, so I'm just going to swap out now to do a quick demonstration of SimScale and what we're looking at. So I want to emphasize that SimScale is truly cloud hosted. All you need to access SimScale is a web browser. So here I've gone from a Google browser and I'm going to the dashboard of my SimScale login. And this basically gives us an SPDM system where we can manage our simulations. I can see a list of all the simulations I've recently run and the activity. And obviously we can search in here to find the simulations of interest. So if I'm looking for a compressor, we're looking at this compressor geometry today. Obviously, in this collaboration with Datadvance, we've run everything through the API. But just to give you a flavor of what's possible in SimScale, I'll just show you this simulation through the graphical user interface as well. So we can see the impeller here, and we could have a look at the simulation runs that have been run on this impeller to analyze the results. So crucially here, we want to look at the temperatures and the pressures that are created during this simulation, and also the force, so that we can understand the power that is produced, power that is consumed by this impeller. So we can analyze individual values out of here from the velocity. We can see the higher velocity at the extremities of this impeller and the pressures as well. We can add cutting planes if we want to analyze what's going on inside the model itself and pick out individual values if we want to understand how this is actually performing. We can see the flow coming in the inlet, going round, and there's obviously a rotational component to that flow as it exits from the impeller. So we can understand how our design is actually functioning. We can obviously analyze pressure, temperature, and velocity of this simulation so that we can get a full picture. Okay, so to actually set up a simulation, it's very straightforward as well. As an example here, I'll duplicate this previous simulation that we had. And say we've got our optimal design now. Maybe we would want to run a parameter study where we look at different flows. So we could have a look at the velocity outlet where we've got 1.5 kilograms per second. And rather than doing an individual point, we could actually set up multiple points in here, multiple flow rates that we want to analyze and set off a design study here. So we could copy that in from a table or just create the table live here in SimScale. And SimScale then recognizes that we're doing a design study and sets off an experiment run where we're using all of those flow rates to run 5 simulations in parallel, and we'll have the results back from that in a few minutes. Okay, so that's all I wanted to do to introduce SimScale at this point. We'll now switch back to the slides that we were looking at, and I'll hand over to Laurent at this stage to give us an introduction to Datadvance.
Thank you, Steve. Hello, everyone. Nice to be part of this webinar session. Let me share my screen. Okay, so I'm going to talk a little bit about the company first and what we do at Datadvance, how we complement the SimScale offering, and more precisely on this, thanks to that use case, we're going to show the complementary aspects of the two solutions. First of all, the company Datadvance is a software editor. So we develop quite advanced software technology in the field of mathematics. So we are experts in design space exploration as well as predictive analytics, so predictive modeling, machine learning, and artificial intelligence. Datadvance is actually a spin-off of the well-known industrial company Airbus, incorporated in 2010 as, let's say, the result of a collaboration between Airbus and a quite famous research center in Russia. That was back in the days where Airbus was deploying in various offshore countries, so including Russia, and they had detected a quite advanced research center in applied mathematics called IITP, which stands for Institute for Information Transmission Problems. These guys own 3 Fields Medal since a few decades, so quite high-level mathematics. And they started this collaboration in the field of just algorithms for predictive modeling, so machine learning, artificial intelligence, and design space exploration methods, essentially optimization. So they joined forces, and it gave birth to Datadvance. And since a few years now, we are now totally independent software editor, and we sell our technology to all the industries. The technology is absolutely not specific to any industry, not aerospace, not automotive. It works in all contexts where you have simulation or pure data. So on the screen, you have the main pillars of our technology. The first one is engineering workflow automation. The goal here is to capture an engineering workflow, multidisciplinary engineering workflow, so that we can run it completely automatically. So without man in the loop, meaning that we can enter statistical or looping with that workflow, which open doors in terms of statistical analysis, and as you can imagine, design space exploration, because by looping we can evaluate various combination of the parameters that define a given system. So the first pillar is this engineering workflow automation, how to orchestrate a multidisciplinary engineering workflow. The next pillar is design of experiments. So it's now getting closer to the notion of predictive analytics, because before you are able to produce a predictive model, a black box mathematical model that represents a physical behavior, you need to evaluate various combination of your parametric system. So that's exactly the concept of design of experiment. We in a very smart way, try to pick some combinations of parameters defining a given system, whatever the system is. Today, it's going to be an impeller or rotating machine. It could be a satellite, a car, whatever. As long as it's parametric, we can play a role here. So we have quite advanced algorithms that can do a very smart sampling. So just by evaluating a limited number of combinations of your parameters, we can then go to the learning phase based on the database we have produced, thanks to design of experiments, to then run some machine learning and AI technology then to produce predictive models. So this is the next pillar here. And these predictive models are extremely useful in engineering because they can substitute to very expensive and heavy models, or they can complement it. We can use them in combination in a hybrid mode with high fidelity models. In any case, it speeds up the engineering process, because a predictive model provides a feedback or an answer in just a fraction of a second. So you can imagine you can loop over million times or thousands of times on various combination of parameters. The next pillar is about optimization. So we have developed in-house very advanced optimization algorithms, new generation algorithms developed in the last 10 years. It's very advanced and allows us to tackle any kind of optimization problem, whether your parameters and variables are continuous, discontinuous, categorical, whatever, or if you have a noisy problem or a model problem, we can, with multiple objectives or single objective, we can address that with our technology. And finally, the last pillar is about uncertainties. How to take into account uncertainties and variability in a given system definition. So that's the science of uncertainty quantification that we can actually couple with optimization to do robust optimization. So all of that is part of the pSeven solution that we develop at Datadvance. The particularity of the latest version of pSeven is that version runs in the cloud. It's a native full cloud, let's say, collaborative environment. So as for SimScale, you just need a web browser to use it. You just need a web browser to build a workflow. You just need a web browser to run the workflow and exploit the results. So that's what you're going to see today. So experts, engineers can build their workflows representing a given engineering methods. And this is represented by such a block diagram representation. And once the workflow is ready, then it can be actually packaged into easy to use web apps. So that's the concept of Apps Hub. And you have a snapshot here of the interface, what it looks like. It's quite, by the way, similar to what you've seen from Steve's slides, with some small icons like this that can drive you to the application. So behind this, you have a very simplified web interface to prepare a simulation. So in other words, to prepare the workflow execution. So this environment runs in the cloud. It can be deployed also on premises. So if you need to be in a secured environment without connection to the internet, and this really allows you to enter collaborative engineering and design space exploration. So I'm going to stop here and then pass the ball to now to Nikita, my colleague, who will show you how the system works and behaves.
Yeah, thanks, Laurent. Oh,
So
hi, everyone.
I'm giving you the ball. You are presenter now. Yep, thank you.
So I'm going to show you technical part of this webinar. So here are contents. First of all, we'll look at the optimization problem statement and our case. Then we'll look at what cloud-based solution we've prepared for this optimization problem and what results we got with this solution. So currently, turbo machines are very common in various industries, starting from aerospace, energy, up to automotive, and lots of others. Lots of manufacturers of small turbo machines and big ones. And one of the main goals now is to deliver the best product to the market on time and on budget, which directly leads us to the optimization problem with the help of engineering software tools. Big companies like Rolls-Royce or Siemens use in-house CFD simulations as a daily routine for several decades. For them, cloud technologies could help drastically reduce simulation costs. And at the same time, cloud technologies may allow small and middle-sized turbomachinery companies to get access to CFD technologies. So with the help, for example, of SimScale, which was just not the case even several years ago. And it allows such companies to deliver their devices, their compressors to the market faster and on budget. So the main goal of our work was to create a cloud-based optimization workflow for turbomachinery needs. And for this case, we've prepared as a classic optimization problem, optimization of the air compressor efficiency. So here, polytropic efficiency was used as a target function. We wanted to maximize its value. Compressor operational mode should stay the same for the optimal geometry. So the pressure drop here was used as a constraint. And compressor blades profile was varied during the optimization process. So we got 4 geometric parameters already mentioned by Steven. And here the overall structure of the prepared solution is demonstrated on this slide. So here pSeven Enterprise was used as a cloud-based platform for the optimization workflow creation. On each iteration of optimization cycle, a classic sequence of CAD and CAE was executed. SimScale was used here as a full cloud-based CFD solver. Optimizer by Datadvance was used and executed in the cloud too. And Siemens NX was used as a CAD tool, which was executed on the local workstation, connected and managed by pSeven Enterprise. So the combination of local and cloud-based parts is presented in this workflow. We intentionally kept legacy local CAD tool because we know that many turbomachinery manufacturers heavily rely on Siemens NX in particular. So they have licenses, they have it installed locally, and etc. However, you can substitute this tool with another cloud-based like Onshape, so the overall solution to become fully cloud-based. So let's take a look on CAD and CAE models in more details. First of all, a CAD model, as I've already mentioned, it was prepared in Siemens NX. We didn't use a point-wise parameterization of compressor blade because it's rather inefficient. So we've prepared a special reparameterization of the compressor blade's profile. The blade's camber curve was controlled by 4 different geometric parameters: alpha, gamma, H1, and H2. And you can see on this slide how these parameters influence the camber curve of the compressor blade. So this parameterization allows us to generate wide variety of impeller geometries. And here you can see 2 different examples which are pretty different from each other. Here is a CFD model. Steven already talked about the simulation setup, so I won't stop here. Just highlight one more time that the flow here was compressible, steady state, and fully turbulent. And some more details on the CFD model. We've used, the model was executed and sold with SimScale in the cloud, and we used 16 cores in SimScale to simulate for this case, which led us to 3 minutes of simulation time. Convergence, numerical convergence was controlled and obtained for each simulation within 500 iterations. And here we can see CFD results for the initial compressor geometry, the fields of pressure and temperatures from SimScale. And the initial polytropic efficiency was 91.3%. So let's take a look on the optimization workflow that was prepared in pSeven Enterprise. So here it is. You can see here lots of blocks. Each block on the scheme represents some simulation procedure, like execution of a CAD tool, launch of a CE simulation via API of SimScale, and launch of optimizer. So different blocks, and all these blocks are connected with each other by links, which represent the logic, the sequence of the workflow execution, and also they show how the data is transferred between the blocks. Some of the blocks are executed in the cloud, like SimScale or our optimizer, and other blocks are executed locally, like Siemens NX. This workflow was packed and published as a special simulation web application to the Apps Hub. It's a special storage of web applications in pSeven Enterprise, which I'm going to show you now. So here you can see pSeven Enterprise. You access to it through the browser. Here in the working field, you can see our optimization workflow, different blocks, optimization, and a single round composite block. It was, as I already mentioned, packed as a special web application. And we're going to dive in Apps Hub. So here you can see storage of different web applications prepared by automators in pSeven Enterprise. So all users of pSeven Enterprise can access to this web applications and use them to launch their simulations without going deep inside the simulation workflow. So we pick this one for our case. We can download it or we can open it. We open it now and we see user interface of this web application, which will be available for all users to use and to launch. And here we can see brief description of this application. We can expand it and see the optimization problem statement and some instructions how to use this application, how to launch, how to extract results, and etc. You can configure your run before the calculation is started. So here you can change the optimization budget and the boundaries of geometric parameters within which you want to vary them. Also, SimScale API parameters like API key or project ID also may be changed within this user interface. So we've configured run and we press calculate button. I've skipped this part in the demo. So here we've got results. We can see optimal values of polytropic efficiency, as well as geometric parameters. We can see that optimization status is okay, so everything is good. And we can download results of the optimal geometric model of the compressor and reports with the optimization history. So we'll download it now and look at the report. So it's a report in the form of an HTML page, but anyway, you can generate also a CSV file or any others which you want. And here you can see all the data, all the optimization history, different plots, 2D, in parallel coordinates, and etc. So it's interactive. And also correlation metrics between inputs and outputs is added here. It's needed to say that everything here is customizable, so it's not fixed by pSeven Enterprise. You can change your UI of your application and files that you want to generate form of reports the way you want. So it's just an example. And in this work, we've used the prime optimization technique developed by Datadvance. It's a surrogate-based optimization or SBO. In this method, a surrogate or approximation mathematical model is built and used instead of the heavy computational model during the optimization process. By a heavy computational model, here I mean a CFD model. To keep results correct, the approximation model is continuously updated during the optimization process. So this method is preferable and was developed specially for real engineering problems with their typical issues like high nonlinearity, multimodality, noisiness of response surfaces, and etc. One more important feature of SBO is that it is a budget-based method. So the optimizer won't use more heavy CFD model launches than user allows to. So in this case, we've used 120 iterations at the budget value, which led us to the optimal results. We can see that the polytropic efficiency was increased by 1.6%, while the outlet pressure stayed almost the same. So our optimal value is within constraints. You can see optimization history, how the optimization process converged during iterations. So the optimal value was obtained after within 40 iterations, as you can see from these plots. And here are results of CFD simulations for initial compressor geometry and optimal compressor geometry. Here are the pressure fields, and the differences between two fields are not very big due to the fact that polytropic efficiency is highly sensitive to values of pressures and temperatures both on inlets and outlets. So for the optimal compressor, outlet temperatures are higher than for the initial compressor geometry. And the same is for temperatures. So in this work, we've developed a cloud-based solution for turbomachinery needs, an automated simulation workflow, and a special simulation web application with user interface for air compressor optimization. This solution may be used, for example, by compressor engineers during the design process to get the optimal compressor geometry. Of course, this is just an example of how cloud technologies may be used in engineering practice. These cloud-based tools, pSeven Enterprise, the platform for simulation workflow preparation, and SimScale as the CAE tool may be used not only for this case, but for many others. So thank you for your attention. And I pass the ball back to Steven.
Great, thank you, Nikita, for that really informative presentation. And thank you, Laurent, for the introduction as well. That was really good. So what have we seen there? So actually, first of all, we've had some questions come in. Please feel free to submit some more questions. We've got some more time to answer your questions. But the other thing that I want to touch on is just say what we've seen. So far, we've seen an end-to-end shape optimization that uses Datadvance's pSeven to drive and optimize the geometry based on the efficiency results and the surrogate-based model. The simulation results were produced in SimScale through the API, and the total design space was reduced from potentially 160,000 simulations to the budget value that Nikita mentioned, the 120 simulations to find the optimal geometry and the most efficient impeller. So hopefully you enjoyed that collaboration. We've certainly enjoyed working together on this project, and it's been really good. So we've got some questions come in. So the first question that I've got here is actually relevant for you, I think, Nikita. So the first question is it possible to integrate our in-house tools into the optimization workflow? So I assume they mean their CAD tools.
Yeah, it's absolutely possible, and moreover, pSeven Enterprise was specially developed to make it possible to integrate almost everything that you may launch on Windows or Linux machine. So in this example, with integrated special custom reparameterization tool, which was executed on the Windows machine. It's Blade Guion, so it's shown here. So it was used to reduce the dimensionality of our optimization process, just to not to use a pointwise parameterization, but to reduce it to 4 geometric parameters. And it's just an example. You can like embed almost everything. So thanks for the question.
Great, thanks, Nikita. There's actually a follow-up question associated to that. Someone has asked, how does it interface with the CAD software? Do we need to develop an API?
So pSeven Enterprise has both embedded integration blocks, which are developed by our team, and they are published with the platform. You can use them as is. So all API things, all integration things are embedded there and done for the user. But if something is missing, if you want to add something new, like this in-house tool, you can develop your own integration blocks. So we have quite simple block API. that allows you to develop your own integration tools and to use them in pSeven Enterprise and to share them with all users, all other users. So they'll just be a part of the library or library of blocks, I mean.
Great, thanks. So there's a question coming specifically around the simulation as well. So someone's asking, how did this optimization use cyclic symmetry of the object? So I'll take that one. Of course, this simulation could have used cyclic symmetry, but actually there wasn't much of a reason to use cyclic symmetry in this situation. The simulation was quite fast and straightforward. As Nikita said, the simulation that we were running here only took 3 minutes to complete using the entire geometry. Obviously, if it was a much more complex geometry, you could benefit from using symmetry. So actually, I'll just switch out to the simulation that I set up during the demo. And we can see that those 5 simulation runs in the experiment, they actually ran in parallel within 6 minutes. So the results are actually available very quickly from the cloud to be able to use. Okay, there's another question around how the costing works. So someone has asked, how does the costing work in terms of optimization runs, limit number of runs? So as Nikita mentioned, within pSeven, you can set a limit on how many runs you actually want to run. And if you've run one in advance in SimScale, you know how much it's going to cost from the core hour consumption. So we saw there that one simulation run consumed about 1 core hour. So in this circumstance, it costs very little, almost an insignificant cost in terms of cents per simulation run. Okay, so there's another question here for Datadvance come in. So the question is the graphical user interface fixed in pSeven, or can I customize it?
Yep, thanks for the question. As I've already mentioned, everything concerning user interface or even blocks is customizable in pSeven Enterprise, so you can build your own user interface from nothing for your web application, or you can use a template user interface that was shown now. So it's used in platform. It's embedded in the platform, but no restrictions here for the type of user interfaces. And one more thing, not only web applications may have interfaces, but also the blocks of how you can configure them in edit mode. And blocks also can have a customizable user interface. So it's a highly customizable platform in this in these terms. So thanks for the question.
Excellent, thanks, Nikita. So we'll just give everyone a chance to send questions in, and obviously now it's over to you in the audience. You can request a demo from SimScale by visiting our website or contacting us directly at sales@simscale.com, and we'll get back to you within a day or so, and someone from my team will be able to provide you with a demonstration. And Laurent or Nikita, do you want to cover from the Datadvance side how people can get in touch?
Sure, thank you, Steve. But yes, so same story here. So from the Datadvance side, please do not hesitate to get back to us if you are interested in a test. We provide 60 days assisted trial licenses. Usually we have of course a discussion on your specific interest or potential use case, and we help you to put together the entire proof of the concept or example, yeah, it has proven to be very efficient way forward. So do not hesitate. The website also provides a lot of information regarding very high-level features and information about these features. But we also provide the documentation online. So if you're curious about the basics of pSeven Enterprise, then do not hesitate to go to the website. You'll find there a bunch of interesting documents.
Excellent, thanks, Laurent. So I think we've got time for one more question, one that's come in recently about pSeven. Is someone's asking if it's available in a SaaS model. So I guess they're just interested in what license models are available.
Yeah, thanks for the question. It's a typical one. So the answer is no. We don't provide the software in SaaS mode. It's provided as a packaged software, so you can deploy it on any cluster, so Kubernetes cluster, so you can deploy it on public cloud like Amazon Web Services, Azure, DigitalOcean, etc. You can also, and that's something which is really key, especially in some critical business area like defense, you can deploy it on premises. So you just have to deploy the package using Helm on your Kubernetes cluster and within this secured environment if needed. But we don't provide the SaaS access, and it might be the case in the future, but not short term for sure. For now, it's packaged software.
Okay, great. So that's all we've got time for today. Thank you everyone for your attendance, and the recording will also be going out if you've got any colleagues or friends that weren't able to attend. So thank you again to Laura and Nikita for your presentations, and we'll see you next time.
Thank you, Steve and Monique and Valerio. That was great, and we look forward to hearing from the attendees.
Yep, thank you everyone for your attention.
Thanks. Goodbye.
Bye.
Bye.